Golden Iris Productions presents A Journey Through History, Understanding Science by Mark F. Dennis. Part 1. A Quest for Knowledge. Setting the stage. If you've been following this channel, you know we're tracing how ideas about nature evolved. This episode is a quick journey from ancient philosophy through the scientific revolution to Einstein and the dawn of quantum theory. We'll keep the focus on the turning points. Ancient Greek foundations. The early Greeks asked what the world is made of and how it behaves. Thinkers like Democritus imagined tiny, indivisible units, atoms. Many also saw the cosmos as ordered and intelligible, reflecting a rational design. Cosmos and cycles. To the ancients, the heavens displayed regular cycles that gave nature its rhythm. Seasons, planetary motions, and eclipses suggested a universe that could be understood through reason and geometry. The medieval synthesis. Through the Middle Ages, scholarly thought often placed Earth at the center. Philosophy and theology were intertwined, and the cosmos was read through accepted authority as much as observation. Copernicus and Kepler. Nicolaus Copernicus proposed a heliocentric system. Earth orbits the Sun. Johannes Kepler refined this with elliptical orbits, linking precise observation to mathematical law. The center of the cosmos, conceptually, began to shift. Galileo, evidence first. Galileo used the telescope to put ideas to the test. Moons circling Jupiter showed not everything revolves around Earth. His defense of heliocentrism led to conflict and ultimately house arrest, but the method endured. Newton, a unified mechanics. A century later, Isaac Newton formulated the laws of motion and universal gravitation. He unified the falling apple with the orbiting moon under one mathematics, founding classical physics and a new predictive power. The Aether hypothesis. By the 19th century, many physicists believed light waves needed a medium, the luminiferous aether. It was thought to fill space, carrying light the way air carries sound. Michelson-Morley, a null result. Albert Michelson and Edward Morley tried to measure Earth's motion through the aether. Their famous experiment found no such effect, no detectable aether wind, shaking a core assumption about light. Einstein, space, time, and gravity. Einstein's special relativity made the aether unnecessary. The speed of light is constant for all observers. General relativity reimagined gravity as the curvature of space-time, shaped by mass and energy, explaining planetary motion in a new way. Toward quantum theory. Einstein's breakthroughs helped open the door to quantum mechanics. Physics moved from certainty to probability, where particles behave in ways that defy everyday intuition, yet match precise experiments. Closing. Our scientific story is cumulative. Each generation questions, tests, and refines what came before. From atoms and cycles to space-time and quanta, the drive to understand nature only grows stronger. Thanks for watching. Let's keep exploring. Golden Iris Productions presents A Journey Through History, The Road to Relativity by Mark F. Dennis. Part 2. The Dawn of Modern Physics. Introduction. The Mystery of Light. By the late 19th century, physics faced a deep puzzle. Classical mechanics worked well for everyday motion, but Maxwell's equations predicted that light always travels at a fixed speed, no matter who measures it. This result clashed with Newton's ideas of absolute space and absolute time. Galileo and Newton, the old foundation. For centuries, motion was understood through the ideas of Galileo and Isaac Newton. Galileo taught that the laws of mechanics look the same in any smoothly moving frame, and Newton extended this into a complete physics based on absolute space and absolute time. This framework dominated science for more than 200 years. Maxwell's new challenge. In the 1860s, James Clerk Maxwell unified electricity, magnetism, and light into one elegant theory. His equations had a surprising consequence. The speed of light appeared as a fixed constant built into nature. This raised a troubling question. Constant relative to what? The ether, a medium no one could find. To explain light's behavior, physicists proposed a mysterious medium called the luminiferous ether. Light waves were believed to travel through it, much like sound travels through air. If the ether existed, scientists should have been able to detect Earth's motion through it. Early experiments, Fizeau and others. In 1851, Hippolyte Fizeau measured how light travelled through moving water. His results hinted that something was off about the traditional wave through a medium picture of light. Still, the ether idea persisted. The Michelson-Morley shock. In 1887, Albert Michelson and Edward Morley conducted the most precise measurement yet to detect Earth's motion through the ether. The result was stunning. They detected nothing at all. Light speed appeared completely unaffected by Earth's motion, a result that shook the foundations of physics. Lorentz attempts to save the ether. To explain the puzzling experimental results, Hendrik Lorentz proposed that objects physically contract when moving through the ether. He also introduced the idea of a local time that differed between moving observers. These fixes preserved the ether mathematically, but at the cost of increasing complexity. Poincaré strengthens the mathematics. In 1905, Henri Poincaré refined Lorentz's ideas and presented the Lorentz transformations in their modern symmetric form. He moved close to a true relativity principle, yet continued to maintain belief in the ether as a physical medium.
Einstein's breakthrough. In the same year, Albert Einstein took a radical step. He removed the ether entirely and built physics from two simple postulates. First, that the laws of physics are the same in all inertial frames. Second, that the speed of light is constant for all observers. From these ideas, he rebuilt our understanding of time, space, and motion. A new reality emerges. Einstein's theory led to astonishing conclusions. Moving clocks run slower. Objects contract in motion. Events that seem simultaneous to one observer may not be simultaneous to another. And the theory introduced the profound unity of mass and energy, expressed in the famous equation E equals mc squared. Minkowski's spacetime. A few years later, Hermann Minkowski reframed Einstein's ideas into a four-dimensional geometric structure called spacetime. Space and time were no longer separate entities, but woven together into a single continuum, forming the foundation for 20th century physics. Conclusion. The road to relativity was not a sudden discovery, but the culmination of decades of experiments, contradictions, and bold insights. Einstein's 1905 theory finally resolved the clash between Newton and Maxwell, and forever changed our understanding of the universe.
Einstein and Special Relativity, Part 3. Golden Iris Productions presents A Journey Through History, Einstein and Special Relativity by Mark F. Dennis. Part 3. How Einstein Created Special Relativity. A Physics in Crisis. At the dawn of the 20th century, physics was divided. Newton's mechanics described motion, while Maxwell's equations described light. But the two theories didn't agree. This growing contradiction signaled that something fundamental was missing. Einstein's early curiosity. Einstein's journey began with a simple question. What would it be like to chase a beam of light? This childhood thought experiment stayed with him for years and eventually led him to challenge the foundations of physics. Chasing a light beam. If Einstein could catch up to a light wave, it would appear frozen in space. But Maxwell's equations say such a wave cannot exist. This contradiction convinced Einstein that our assumptions about time and motion must be wrong. The ether problem. Physicists believed light travelled through a medium called the ether, but experiments like Michelson-Morley failed to detect it. Einstein took this seriously and asked a bold question. What if the ether simply doesn't exist? Two postulates. Einstein built his theory on two simple ideas. First, the laws of physics are the same in all inertial frames. Second, the speed of light is constant for every observer. These postulates were simple, but their implications were revolutionary.
Time becomes relative. If the speed of light is constant, then time itself must adjust. Einstein showed that moving clocks run slower and that events simultaneous to one observer may not be to another. Time became a dynamic part of physics. Space contracts. Einstein demonstrated that objects contract along the direction of motion. Space was no longer rigid. Together with time, it formed a unified structure that adapts to preserve the speed of light. Lorentz transformations reinterpreted. The Lorentz transformations had been invented to save the ether. Einstein showed they were not ad hoc fixes, but the real rules governing space and time. They described how the universe actually behaves. Mass-energy equivalence. From his new framework, Einstein discovered that mass and energy are interchangeable. This insight, expressed in the famous equation E equals mc squared, revealed a vast reservoir of energy hidden within matter. Minkowski's spacetime. Hermann Minkowski reframed Einstein's ideas into a four-dimensional spacetime. Space and time were no longer separate entities, but woven together into a single geometric structure. This became the foundation for the 20th century physics. A new universe. Special relativity replaced the old absolutes with a universe where measurements depend on motion. It resolved the conflict between Newton and Maxwell and revealed a deeper, more elegant structure beneath reality. Conclusion. Einstein's theory did not emerge from new experiments, but from clarity, logic, and imagination. By questioning long-held assumptions, he transformed our understanding of space, time, and energy, and opened the door to the physics of the modern age.